Hi everyone, today I am presenting my work on quantifying the predictive uncertainty of regression GNN models under target domain shifts. This work has been done at Basira Lab by Selim Yürekli, Mehmet Arif Demirtaş, and supervised by Dr. Islam Kik. The problem that we would like to solve is, given a brain connectome graph, how to quantify uncertainty of the predicted IQ score under target domain shifts using ensemble of GNN models. To be more specific, we have a brain connectome graph map and we want to find an uncertainty value for the predicted score using ensemble of GNN models. There are many studies related to predicting uncertainty under target domain shift. One of them proposed Bayesian neural networks are effective when quantifying uncertainty in the context of medical image segmentation. However, Bayesian neural networks are difficult to train and have a heavy modification in its architecture. Another study proposed a deep ensembles in order to estimate uncertainty value under target domain shift in the context of dataset shift. However, this study doesn't include graph neural networks when building the ensemble. All of the state-of-the-art methods do not handle uncertainty prediction under target domain shift using GNNs. Before we start our proposed framework, let us explain the domain shift phenomena. Let's say we have a dataset and we want to split them into train and test sets. At this point, domain shift phenomena occurs when train and test distributions are completely different from each other. This is the case that we want to identify by predicting uncertainty score as well as IQ score prediction. Since this work explored uncertainty under domain shift, we first created an algorithm to pre-process dataset and simulate domain shift. At the beginning, we have a set of brain connectome graphs. Then, we divide the whole dataset into three parts by giving them to a clustering algorithm. You can see the algorithms that we used to cluster in the red box at the bottom left. Please note that after clustering whole dataset, clusters distributions become completely different from each other. After that, we put two of them into train set and last one into test set. Finally, we obtain differently distributed train and test sets. Here is the schema of ensemble construction part. Suppose we have a brain connectome map and want to estimate uncertainty as well as IQ score. We construct ensemble with regression GNNs having an input layer, graph convolutional layer, null layer, and dropout layer. We diversify the base learners in ensemble by changing the parameters like layer dimensions or size of layers or dropout rates. We provide connectome map to already trained regression GNNs in ensemble independently. Each of them will have an IQ score output. Then we calculate IQ score standard deviation. Calculated standard deviations will be our predicted uncertainty score for given connectome map. Here is the general schema of our work. We are given a set of brain connectome graphs. We cluster them into three groups using k number of clustering algorithms. After creating three different train and test sets for each algorithm, we perform training of the already constructed ensemble with the connectomes in the train sets. Next, test set is provided to a trained base learners in ensemble. Then, the uncertainty values resulting from test sets are kept in a vector. We repeat this process for each clustering algorithm. Finally, we take the row-wise average of the elements in the uncertainty vectors. At the end, the final uncertainty vector is determined for all subjects. Here is the proposed metric in order to compare ensemble success in terms of uncertainty accuracy. The idea behind the formula is if the prediction of a target score results in a high mean absolute error for any subject, then the model should have a high uncertainty and vice versa. Likewise, if the prediction of uncertainty results in high certainty, then the mean absolute error should be low. In our experiment, we used Opsin Brain Imaging Data Exchange dataset with 202 subjects. Each subject is represented by a functional brain connectomes that is parcellated 116 rows. To measure the predictive uncertainty of the deep graph ensembles without domain shift, we trained and tested each ensemble using three-fold cross-validation. In domain shift simulations, We clustered overall dataset into three groups using clustering algorithms: k-means, affinity propagation, BERT, agglomerative clustering, and spectral clustering. We trained 8 ensemble models with varying architectures and parameters. Our ensembles are constructed only from regression GNNs, which are regGNN and PNAnet. The ensembles are compared according to mean absolute error and proposed metric in both cross-validation and domain shift cases. Here are the results of the experiment that compares the ensembles by mean absolute error. Before going through the chart, you can see the details of the ensembles. Here you see the results of ensembles under cross-validation. We can clearly observe that ensemble 3, 5, and 8 perform better than other ensembles under cross-validation. However, the ensemble 3 and 5 failed to show the same performance under domain shift. The lowest error in domain shift case belongs to ensemble 8. Therefore, we can conclude that ensemble 8 has the best performance among others under target domain shift in terms of mean absolute error. On the other hand, here is the result that compares ensembles in terms of proposed metric in this research. As in both cross-validation and domain shift cases, again, ensemble 8 performed more successful than other ensembles. To sum up, we proposed a deep graph ensemble method with regression graph neural networks for quantifying the predictive uncertainty caused by target domain shifts. Moreover, we proposed a novel predictive uncertainty measure to quantify the uncertainty of an ensemble. Our experimental results showed that the ensembles using diverse regression GNNs reduced the predictive uncertainty error in both cross-validation and domain shift. In addition to these, ensembles, including only regGNN, tend to perform more successfully. As our future work, we plan to construct the optimal ensembles automatically using neural searching algorithms from a search space. For more, please visit us at basiralab.com. Thank you.